back from the break. I hope you had a chance to enjoy the morning of the conference, enjoy the food, the networking experience. So question, who did the event quest? Well, actually can't see. Okay, not that many. So it's a gamified experience where you can write talks, check out the venue. And the other thing is you can enter a raffle from the leaderboard to win vouchers that we got from the Linux Foundation for a training tomorrow. So maybe interesting to check that out. Now, coming to our next speaker, the first Viennese, actually. I'm not. And yeah, and he's a bit of a false advertising. If you look at his hoodie, it says eBPF, and he's from Isovalent. But he's not talking about eBPF. In fact, he's going to talk about CRI, Container Runtime Interface, and writing it from scratch. Filip, the stage is yours. Applause for Filip Nikolic, please.
Thanks so much. Thanks so much for the kind introduction. As already mentioned, it's a bit of false advertisement, right? So if anybody here is thinking about eBPF and wants to learn more about it, there's other great talks about it, and you can definitely catch me on later on during the conference. I'll be around. But what I really want to focus on for today is the Container Runtime Interface. That's what CRI stands for. And there's a couple of topics involved here, and you'll understand as well why I want to talk about this and what it has to do with certain other things that I'm doing. So as mentioned, I'm actually working at Isovalent, which is now part of Cisco, and we have a project called Cilium, which is a CNI. And believe it or not, but CRIs and CNIs, I know there's a lot of acronyms being thrown around here, but they're really, really tied together. And you'll understand in a bit why that is the case. But first, I would like to start with a game. If possible, everybody, please raise your hand right now. Please, everybody raise your hand and leave it up there if you've ever heard of containers. If you heard of containers, it can stay up there. And now, if you know what a CRI is, leave it up there. Okay, some hands are down. If you know what gRPC is and how it works, leave it up. If you know what Linux namespaces are and how they work, leave it up. If you know what a CNI is and how it works, leave it up. And now, last but not least, if you have ever coded in all of these things, please leave it up. Okay, so we basically went from all the hands up to none of them. And this is the challenging thing about this presentation, because we need to understand all of these topics in order to get through this talk. So as you can see, it's not really the best thing to do all of that within 25 minutes. So we'll kind of do it like a speed run, all right? We'll start with CRI and Container Runtime. What exactly do those terms even mean? So what they mean, CRI stands for Container Runtime Interface. Okay? Oftentimes, what you associate with a CRI are projects such as CRI, projects such as Containerd. Technically speaking, that's not really accurate. They're actually container runtimes and not container runtime interfaces. They're implementing the interfaces. I know that this confuses a lot of people, just saying it like this, so I have a couple of explanations with pictures here for you. What we can imagine is a user just sending over a YAML file, right? You want to deploy a pod somewhere, and so you're sending over a pod, a container called best app ever, and you send this over to the Kube API server. The API server is going to do whatever it needs to do, right? It talks to a couple more of things within the Kubernetes aspect. And so at some point, the scheduler would tell it, hey, this is the node that I want you to let this run on. And so it will then contact the kubelet on that specific node and tell it, hey, here is this container that I want you to run. And the kubelet doesn't actually do the job. Many people think that kubelet is the one creating the containers, but that's not the case. That's actually the job of the CRI. So the kubelet is basically forwarding the request to the CRI. But that's not entirely accurate. Now, this is just something where I'm a bit pedantic about it. So technically, it's the container runtime that is creating these things for you. And the CRI is actually the thing in between it. So the CRI is really just an API that defines how the communication between the kubelet and the container runtime are supposed to happen. What exactly can you send over? What can you expect as a reply? Stuff like this. So that's what the difference is. However, since everybody loves acronyms, usually you just call it a CRI for these kinds of reasons, right? People feel smarter and better when you use acronyms rather than the proper names, so that's what we're going to do within this talk as well. And the CRI is then going to create the container for you, and that's pretty much it. Okay, so this is the differentiation between what a CRI is and the container runtime. So to summarize, the CRI is the API between kubelet and the container runtime, and it is part of the Kubernetes repository. Okay, you can find it in the Kubernetes repository at staging source k8s io, and then CRI minus API. There it's exactly defined what you need to do in order to be compliant with that specific API. On the other hand, the container runtime is the software responsible for containers. So it receives the tasks from kubelet and it implements that specific API, which is the CRI. All right, so let's go over gRPC quickly, and we'll understand later on as well why this is important. When we think about APIs, one of the most common patterns that many people are familiar with is REST, right? REST APIs. So we have a client, we have a server, the client sends something to the server, like a post request, an HTTP post request on/users, and is then going ahead as well and giving it some data, right? Something like username, something like location, and so on. So this is how APIs usually work. And with REST, it's very simple. Now, gRPC takes this a bit further, so to speak. The idea is still the same. We still have a client communicating with the server, right? It's just that the way how it happens, the way how it occurs, is a bit different. So instead of sending the data as plain text that would be readable if you were to intercept it, it actually is being sent in a binary format, right? This makes it way more compact. It means as well that it's not really readable to us humans usually, but it makes it way more compact, which means, especially in terms of scaling, it is way better because now you do not have brackets in there, you do not have hyphens, columns, commas, spaces, and whatnot. Everything is as compact as it could be. So you're just sending over a sequence of zeros and ones over there, but now you obviously need to understand what do those zeros and ones mean. So the client and the server both need to have an understanding. Does this zero mean that is it the name? Is it the username? Is it the location? Or does it start somewhere else? How exactly does this work? And gRPC uses HTTP as well. It usually just uses a newer version of HTTP. And I took some artistic liberty here. You can see that as well I put up there create user and brackets. Well, that's because the slashes do not really matter anymore as we usually know them from REST API, right? We would usually do a post in /users for a REST API. We don't really bother with that at gRPC. Rather, we're calling a specific function. And that function is not something that you really see. It would be encoded within the binary data format that we took here, but it's easier to understand it a bit if I was to say here, post create user. But the important aspect here is client and server need to understand these zeros and ones. So how exactly does this happen? gRPU uses for that another technology, which is called protobuf, all right? Protobuf, or protocol buffers, is essentially a format that defines a specific API for you. So you can think of it as its own language, and this actually is a snippet of the actual protobuf file for the CRI, so of that API that we want to look at today. And you can see here it has a service, runtime service, then it has certain things starting with RPC, So those are the different functions that you can do. And then you have messages that are essentially similar to object that many people are used to from languages. So you can see there's many different things, and we would have to implement all of them today, right? We would have to implement all of them in order to be compliant with that specific API. So you can see there in line 3, there is version, line 5, run pod sandbox, line 6, list pod sandbox, and so on. I won't go now into all of these details. We'll look at them a bit later, but just for you to understand what this file means is that we need somehow to translate it now into code. So if we look at these highlighted things here, you can see a runtime service, then version, and it returns a version response. That version response is explained in line 13. So in line 13, we can see that a version response needs to contain the version, the runtime name, runtime version, and runtime API version. Simple, right? And now we can go ahead and pretty much code this in whatever language we want. I simply chose to take Go. But it doesn't have to be Go. You could do this if you wanted to in Java, in Rust, and so on. Oftentimes, there is this idea that everything related to Kubernetes must be written in Go, but that's not really the case. Because of these layers of abstractions that we do have in the Kubernetes ecosystem, you can go ahead and actually choose, for many aspects, different languages if you wanted to. But I stuck with Go here because even if you may not be as familiar with Go, it usually is one of the easier languages to read if you were to just see the code without any prior knowledge. So what we want to highlight here as well are the following things. We have here in line 3, runtime service, which is as well what I highlighted previously. We have here a function called version, and we can see that it returns something called the version response, which is as well the message that we saw there. And we have there the version, runtime name, runtime version, and runtime API version. So we'll just have to follow this pattern for many of these functions that are defined in the API. All right, now let's talk a bit about containers. It's important for us to understand exactly how containers work. There is way too many things here to mention. In essence, they are just a mixture of multiple technologies. Some of them that we won't go over here today are C groups and overlay file systems, which make up images. But what we want to focus on for today's talk are namespaces. There's different kind of namespaces. And please note, when I talk about namespaces here, I'm not referring to Kubernetes namespaces, okay? They're just coincidentally named the same way, but total different things. So there's Kubernetes namespaces, which don't have to do with anything that we're talking about here today, but rather I'm talking about the Linux namespaces. This is a technology that is inside of the Linux kernel. And essentially what it provides you with is a layer of isolation. You have to be a bit careful with that wording because it is not as strict of an isolation as people may think of in terms of virtual machines, for example. However, it is how the kernel does document this specific feature. And as mentioned, there's different kind of namespaces such as PID, network user, mount, and others. But I'm just going to give you an example with PID because it's usually the easiest one to understand, and we'll just focus on the network namespace afterwards as well, as it will be important. As mentioned, namespaces are here for isolation purposes. So the idea is you can assign something, a certain type, depending on the type of namespace that you have, to a namespace. When you do this, it will then only be able to operate within the scope of its namespace. So if we create a PID namespace, which is a process ID namespace, we can assign processes to that specific namespace. So for example, process A and B can be in the same namespace, and process X and Y would be in their own namespace. What does this mean? Well, it means that if you were now to execute a new process, such as PS, which lists you all the available processes, you're going to see just the processes running within that namespace. Simple enough, right? So for the upper one, we would only see A and B, for the bottom one, X and Y. And you can only interact with processes that are in the same namespace as yours. So A could kill B if sufficient permission were to be granted. However, you wouldn't be able to do the same to another namespace because it's isolated, you can't see it, you do not know how you were to reach it, and therefore you can kill it. And the idea is the same with all of these namespaces. And the one that's very important for us for today's talk here as well is the network namespace. The network namespace essentially does the same thing. It means that whatever network configuration you're doing in one of these network namespaces just is going to affect it within that network namespace, but not within the other ones. All right, so in order to now create a container, as you can see, this form of isolation is very important. So the very first thing that a CRI then usually does is it creates such an isolated space, and it creates a so-called network namespace. This network namespace in Kubernetes terms is oftentimes referred to as a sandbox. So within that network namespace, this is what your pod actually is. What's important to understand here is that when you create a pod, you will actually always create at least 2 containers. It's not just one container, it's always at the very least 2 containers. The first container is a container that doesn't do anything. It has an image running in there called the pause image. That image just sleeps forever. And the entire purpose of that container is so that this network namespace is being created. And then you're going to create whatever container you want within that network namespace. This is as well the reason why you can have multiple containers within a pod and why they can communicate via localhost with each other. But this is where a bit of networking comes into place, right? And this is where usually CNI comes into place. As you can see, I'm already talking quite a bit about CRI. So technically speaking, before the container is then being created, the CRI is creating the network namespace. Then it's going to make a call to the CNI, which is going to perform some network configuration within that namespace. And only then we would create the container. If you're interested in this, I'm not going to get into further details here. This is just a very, very brief overview of what a CNI does. I actually have a write-up there that's similar to this talk, explaining exactly what a CNI is and how you could write your own one from scratch for educational purposes. Obviously not really suited for production, but if you want to try it, go ahead. So what we're focusing on is our CRI needs to create this network namespace, and then we want to create the container in. And now let's jump into the code. Now that we have an understanding of all of these things, it's time for us to always check the API, this protobuf file, see what kind of functions are important for us, and now implement them as code. All of this was done in the exact same file. So there's actually a couple hundreds of lines. I think it was about 300 lines of code that this took me. As you can imagine, posting 300 lines of code onto a slide doesn't really make for a readable presentation. And if I was to do a demo and I was to live code 300 lines of code, we would have a lot of errors, right? Admittedly, it would be a lot more amusing to see me fail writing all of this by hand, but this is exactly why I put the important snippets on here. And I'll refer to a GitHub repository later on where you can see the exact code for the entire aspect. So this is a simplified version of the code just in order to show you what the exact important steps are. As we mentioned, the API needs a version, so as we saw previously before, we have a version. The kubelet can call on this version, we return it, simple enough. Now, the next thing is we need to pull an image, right? We do not have enough time to talk exactly about what images are, but what's important here is just quickly think of images similar to archives, right? You may be familiar with file types such as .zip or such as .tar files. So an archive is basically something that you download as a single file, and then you need to extract them as well. Pull image is essentially just downloading that specific archive type. And later on, we can then go ahead and extract it. So whenever kubelet is calling pull image, it is going to try and connect to some kind of registry, download that image, download that archive onto the file system, store it somewhere, and that's it. That's pretty much what we're doing in this function. Then comes one of the special cases, what exactly the CRI needs to do. This is now where we're talking about the sandboxes that I mentioned. So remember, the important aspect of the sandbox, while it has other namespace as well, is this network namespace. So the kubelet will at some point say, hey, please run this specific sandbox now. Now, every sandbox should have a unique identifier, so we're just gonna give it one. We're gonna give it the namespace name minus and then the name of whatever the pod is being called. This is what we're doing in line 2. And this is our unique sandbox identifier, therefore. Then we're going to unpack the image because we pulled an image, and remember the image for sandbox containers is a so-called pause image. This is usually what's always being used. It's just sleeping, it's not doing anything spectacular. So since we have that image somewhere on the file system and it's an archive, we need to unpack it. That's what's happening in line 5. Now, line 8 to 11 is where we now need to modify a couple of things. So we're just modifying some things here. We are taking the file path in order to get the JSON. When you unpack an image, it has a lot of things in there. It has the entire directory structure of that image, including all the executables and whatnot. This is how you're able to start the processes that you want to start in there. And so in there, we will now simply check out this JSON file, which has a lot of configuration, and we're going to set the process terminal to false so that we can actually run this sandbox in the background. After we did this, in line 14 and 15, we can now actually go ahead and run it. In order to do so, we're going to use another tool, which is a low-level API for this kind of things. It's called runc. Runc stands for run containers, and there's amazing talks on this, how you could write your own kind of runc implementation if you wanted to. Essentially, it would mean that you would have to do a lot of unbinding, unsharing, and so on, and you would need to perform a lot of calls with the kernel directly. But to make our life simple, we are depending on runc being installed. And this is something that almost all CRIs out there do as well, such as containerd, cryo, and so on. So you would just tell it, runc, please run this specific image now, and assign it the sandbox ID. That's it. Then we're going to store the information, and we're going to return a response telling it we did what we did. Now it's time for us to create the container. So we now have this sandbox, which is the network namespace, and now inside of that network namespace, we want to create this container. So in line 2 again, we need a unique identifier, a container ID. We're just gonna call it very simply the sandbox ID minus the container name. Therefore, it must be unique. Then we'll go ahead in line 5 to 12, and what we're going to do is we're going to execute runc state, and then we're going to query the state of the sandbox that we just created. Now, when we do this, we will get a JSON as an output. All that we're doing here is we are from the JSON getting the process ID of this sleep execution that is happening, that sleep process. And the reason why we want to do this is because once we have the PID of a process, we can check exactly which namespaces they have. So in line 12, you can then see that in /proc/PID number /ns/net, we are now referring to the network namespace of that sandbox container. And that's important because now in line 15 to 18, we're going ahead and we will again edit the config.json. We'll edit it in such a way that we're now going to override the network namespace. So in line 17, we will just tell it to replace the Linux namespace, the network namespace, with the namespace of the sandbox that we created. Then we're going to save that file, and line 21 and 22, we're going to run it again, as previously mentioned, and we're going to return an output after saving what we did. All of that now needs to start somehow, right? So we have a main function, and inside of that main function, we need to listen on something, right? We need to open some kind of socket, and this is necessary so that the kubelet can send us information. And so we're just opening that socket var run demystifying CRI.socket, and then we're initializing the runtime service with all of these paths. You can see exactly where the images are being stored, for example, what the sandbox image is that we're using, and so on. And then lines 15 to 18, we're initiating this gRPC server, and we will run it. So after we did all of this, let's run a pod. We're simply going to run an HTTPD pod and check kubectl get pods. It will then have the status container creating. So what happens then if we were to do a describe? When we describe that specific pod, after some time, you can see that it will successfully assign that pod to a specific node. Then it's going to pull that image, what the pull image function is for, and then create the container. That's it. And we can see with runc on that node as well that there truly are multiple containers that exist. So we can see the default HTTPD sandbox. This is the one container that only sleeps, and then afterwards we have the actual one. And then with ns-enter, we can check whether everything works as expected. Does HTTPD really do its stuff, right? It's a web server. So we can do an ns-enter onto the number that we see up there. And that specific process ID is just in order to let it know, please execute this in the network namespace with that process. And we can do a curl localhost, see that it works, and we can do so for both of them. All right, with that, thanks so much. And just for you to know, these are the GitHub repositories. On the bottom left, you can see the Demystifying CRI GitHub repository, which is this talk. It doesn't yet have a write-up, but it has all the code that I showed here and even more. And the other one is the Demystifying CNI one that I mentioned. Thanks so much. I think we have time for some questions.
Yes, we have time for, we have 4 minutes. And I always find it fascinating how, a couple of primitives and how many lines of code? 300 lines of code?
About 300, yeah.
Yeah, and it's so much clarity that you gain if you implement it yourself, play around, right?
Absolutely, yeah, absolutely. But unfortunately, the API is quite huge, and you need to implement certain things that aren't really necessary for educational purposes, but they're necessary because kubelet needs it to exist, right? This is why it's a bit more than what I just showed here, but these are the essential pieces. Yeah.
Right. So are there questions? Yeah, I see a question right there. We're going to repeat it for you, please.
Great question. So just to repeat, for the sake of having a microphone, the question was essentially what I showed here was the current CRI implementation, right? So I showed what the API is and how you could leverage this to implement your own container runtime. And the question now was that as well, it's somewhat similar for a CNI. And mentioning the specific company that I'm working for, Isovalent, what exactly did we do in that space? Because the understanding of the gentleman asking the question was that we did some improvements in that area. Essentially, to answer your question is we are heavily relying on the CNI aspect, right? So not the CRI aspect, but as you can see here, the CRI is invoking the CNI. So it is important for us to understand that layer as well, since it's a dependency, so to speak. And the CNI area, we actually did quite some improvements, and some of the maintainers as well are currently working at Isovalent. And we want to design a version 2 of the CNI spec that is a bit closer to what the CRI is. So it would use gRPC and so on to do all of these things. Additionally, there would be some chaining involved and so on. But honestly, to answer all of these questions, it would be faster to just check out the Demystifying CNI repository. It answers a lot more of these questions in further depth. But the CNI and CRI APIs are vastly different, and so it would take too much unrolling right now to get into it, but happy to chat afterwards a bit more about it. But yeah, V2 is supposed to have, for example, something like gRPC as well. Hopefully that's enough for right now, at least.
So maybe a super quick question. Otherwise, thank you so much for this very instructive talk. Let's have another round of applause, please.
Thank you.